Time is not what we think. Scientists have proved your head is older than your feet because gravity slows time itself. Astronauts who spend months in space come back younger than the rest of us, even if only by fractions of a second. Near a black hole, 1 minute for you could be 1,000 years for someone far away. And in the strange world of quantum physics, reality itself flickers, creating tiny loops that may already bend time. If this is true, then the past may not be locked forever, and the future might already exist, waiting for us to step into it. But here's the danger: to travel through time is to risk breaking reality itself. So, is time travel science fiction, or science waiting to be unlocked? Prepare for a journey through the most mind-bending mystery of the universe. We begin. Time, as you know it, feels certain. The second hand glides forward, each beat marking a rhythm no one escapes. Yet beneath that certainty hides a disquieting truth. Time is not as simple as it seems. For centuries, storytellers and scientists have wrestled with one intoxicating question. Can we move through time, not just forward, but backward, sideways, or in loops? We begin not with equations, but with puzzles that sit like splinters in the mind. Imagine, for a moment, finding a letter on your doorstep. The handwriting is familiar. It is yours. Inside, instructions precise and urgent. Avoid that road tonight. Avoid that curve. You obey. And by doing so, you avert an accident that would have cost you your life. The mystery deepens. Who wrote the letter? If it was you, then from what future did you return to place it in your past? This is known as the bootstrap paradox, a loop in which information or objects exist without origin, conjured from nothing, cycling endlessly. Another puzzle, the grandfather paradox. Suppose you journey back and prevent your own grandfather from meeting your grandmother. You erase the line of descent that leads to you, and yet without your birth, who made the journey? The mind recoils at the contradiction. Physicists and philosophers have traced entire families of these paradoxes. The predestination paradox, where attempts to change the past only ensure it unfolds exactly as written. The auto-infanticide paradox, darker still, in which someone travels back with lethal intent toward their younger self. Each story twists the arrow of causality into impossible knots, and yet each paradox illuminates the same thing. Our understanding of time is fragile. Here is a scientific fact, proven and inescapable. According to Einstein's theory of relativity, time is not universal. It bends and warps under motion and gravity. Already, this tells us that the flow you feel is not the same for everyone, everywhere. Your seconds are not my seconds. But here is an oddity, a speculative glimmer. Some physicists wonder if the universe itself might be timeless, that what we call time is only a construct of consciousness, a trick of perception slicing through a frozen eternal hole. In this view, the paradoxes vanish, because nothing ever truly changes. Only our vantage point shifts. It is a radical, unsettling thought. And here is an open debate. If time travel backward were ever possible, does it unravel logic itself, or does the universe self-correct, enforcing consistency? On this question, science is divided. Some argue paradoxes prove time travel impossible. Others suggest paradoxes are illusions, resolved by deeper laws we have yet to uncover. Think of time not as a straight road, but as a river. You drift downstream, carried forward, but rivers meander, form whirlpools, even reverse their flow. Standing on the bank, you might glimpse another bend, another traveler moving ahead of you or lagging behind. Could the river itself contain shortcuts, tunnels beneath the surface, loops back toward the source? The paradoxes are whispers of these possibilities, warnings that if the river can turn upon itself, it may carry more than we can bear. To imagine stepping backward is to imagine rewriting not only history, but identity itself. Who are you, if you can erase the causes that gave rise to your existence? As the fog of paradox thickens, your senses strain. The tick of a clock echoes louder. Each second feels brittle, delicate, as though it might shatter under questioning. The air around you stills, and time seems to hesitate, caught between flowing and folding. In this space of uncertainty, the paradoxes rise not as barriers, but as doors that dare you to ask what lies beyond. And so the journey begins, not with answers, but with mysteries sharpened into riddles. The bootstrap, the grandfather, predestination, and auto-infanticide, 4 phantoms of logic haunting the corridors of imagination. Each points to something astonishing. If time travel is more than a dream, then reality itself must be stranger than fiction allows. But the paradoxes are only the prologue. Behind them waits a deeper revelation, that time is not what common sense believes it to be. To see this, we must leave behind the comfort of clocks and calendars, and step into the fabric that binds all events. For time is not a river running beside space. It is woven with space itself, a single fabric stretching across the cosmos. And once you glimpse its weave, the paradoxes no longer stand as unsolvable. They transform into questions of geometry, gravity, and possibility. Just as you begin to feel the weight of contradictions pressing inward, the scene shifts, the fog lifts, revealing a vast plain of stars suspended in a black canvas. Their light does not flicker with the present alone, but carries histories, some hundreds, some millions of years old. To look upward is to gaze back through time itself. The paradoxes tighten their grip, but now they are joined by evidence all around. Time is not absolute, and it may not be bound. The mind longs for simplicity, for arrows that point in only one direction, but the universe has never promised us simplicity. Instead, it offers complexity cloaked in beauty, riddles hidden in plain sight. The paradoxes do not destroy the possibility of time travel. They invite us deeper, urging us to reimagine cause and effect, origin and outcome. In this opening, you feel both wonder and unease. Wonder that the very structure of reality might allow footsteps into the past, or leaps into the future. Unease that such footsteps might collapse the ground beneath them. The paradoxes are both map and warning sign, guiding us into realms where imagination brushes against law and where the stakes are nothing less than the coherence of existence. From here, the path stretches into Einstein's revelations, into experiments that bend time before our eyes, into visions of cylinders, strings, and wormholes. But we carry with us this first encounter, the paradoxes that unsettle, that linger, that whisper of a universe more intricate than any clock could reveal. And so, as we step forward, paradoxically, into the exploration of time itself, the question remains, are these contradictions signs that time travel is impossible, or signs that reality is deeper than logic alone can hold? The journey has only begun, and already time itself feels less like a certainty and more like a riddle waiting to be lived. Close your eyes for a moment and imagine standing at the bank of a river. The water is wide, its surface shimmering with reflected starlight, its current slow but inexorable. You cannot step out of the river, for you are part of it, carried along from source to mouth. This is how most of us feel time, a ceaseless flow from birth to death, from memory to anticipation. But physics whispers a different truth. Time, it tells us, may not be a river at all. It may be the whole landscape, the banks, the bends, the whirlpools, the deltas, past, present, and future, all coexisting in a vast geometry that does not flow but simply is. This vision emerged from the mind of Albert Einstein, who in 1905 rewrote the grammar of reality. With his theory of special relativity, time and space fused into a single entity, space-time. It was Hermann Minkowski, a mathematician and Einstein's former teacher, who gave the concept its unforgettable imagery. In 1908, he declared, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." With that, the river dissolved. What remained was a four-dimensional fabric, where every event, from the birth of a star to the flicker of your eyelids just now, as its coordinates. Imagine space-time as a vast book. Each page is a moment, laid one after the other in sequence. You are not writing the book line by line, you are already in it, your life stretched across many pages. You, right now, reading these words, are on one page. Your childhood still exists. A few pages behind, your future birthdays are written, pages ahead, even if you cannot yet read them. The flow you feel is the act of consciousness moving through the pages, not the book itself being written anew. Here is a scientific fact. General relativity, Einstein's later work, showed that time is not uniform. It can bend, slow, or stretch, depending on gravity and motion. Mercury's orbit, long a mystery because it did not follow Newton's predictions, became the proof. Einstein's equations revealed that space-time near the Sun is warped, and Mercury, closest of the planets, traces that curvature. The anomaly vanished. The universe had spoken, confirming that time and space are malleable. Now imagine the odd, the speculative. If past, present, and future coexist, then perhaps we never lose the past. Your first breath, the day you learned to read, the moment you looked at a star and wondered if someone out there looked back, all of it still lies written into the geometry of space-time. From this view, death itself does not erase. It only shifts the vantage point. Every page remains. Somewhere in the volume, could an advanced intelligence then navigate those pages at will, visiting moments as easily as flipping to chapter and verse? It is an unsettling idea, yet one entertained even in serious physics, the block universe, eternalism. And here is the debate: is time real, or is it an illusion? Some physicists insist that time is as fundamental as matter or energy. Others argue it emerges, like temperature, from deeper statistical laws. In quantum gravity research, time often disappears from the equations entirely, leaving us to ask, if the universe does not need time to exist, then why do we feel it so strongly? To picture this, let the river return. You float downstream, but now you see it differently. You are not the only traveller. Others drift ahead, behind, even alongside, but you cannot cross their currents. If you could rise above, you would see the entire river at once. Every meander, every pool, every fall. To you in the boat, time flows. To one who sees from above, time is. The block universe challenges not only science, but philosophy. Free will shivers beneath its gaze. If the future already exists, are we choosing our actions, or simply reading our lines in a script written long before? Minkowski's space-time does not forbid agency, but it recasts it. You are both actor and character, both the hand turning the page and the words inscribed upon it. Consider how light carries history. When you look at the Andromeda galaxy, you see it not as it is now, but as it was 2.5 million years ago. That light has been traveling through space-time, untouched, while civilizations rose and fell on Earth. To look at the stars is always to look into the past, yet the block universe suggests Andromeda's present, and even its future, are just as real, written in the fabric though unseen. The imagery deepens. If time is a landscape, then moments are like peaks and valleys, frozen in the terrain. We hike across them, but the mountain range itself does not move. From this, the paradoxes we first met begin to soften. If all times exist, then travelling backward may not undo the present. It may simply be a shift of position, a new vantage within an already written structure. And yet, the mystery lingers. If time is laid out in totality, how do we explain the feeling of flow? Neuroscientists suggest our brains stitch perception into a narrative, one frame after another, creating the illusion of motion through time. Others argue entropy, the increase of disorder, gives direction to the arrow, telling us why memories point backward and not forward. Still others wonder if consciousness itself is the arrow, the flame that burns one page at a time. In this debate lies the wonder of science. It forces us to confront not only equations but ourselves. to ask whether our most intimate experience, the passing of a second, is a feature of the universe or a trick of perception. The stars above remind us that the universe does not hurry. Light takes billions of years to cross its own distances, and yet to space-time itself, no journey is long, no duration is meaningful. From the cosmic perspective, time does not pass. It rests, silent and complete. As you drift deeper into this realization, your own heartbeat seems to slow. You feel suspended, as though the next second will never arrive, yet you know it will. That tension between the eternal and the fleeting is the essence of the human condition. Physics shows us the vast block of space-time. Life ensures we feel only its surface, one moment at a time. And so the river widens, carrying us from paradox into the very fabric of existence. Ahead lies stranger bends, where gravity itself edits the flow, where clocks disagree, and where experiments bring abstraction into measurement. The river does not end here. It carries us further into deeper waters where time bends, folds and stretches, revealing its secret structure. Picture the universe as a vast dark stage, the stars hanging like lanterns in a boundless theatre. Their glow feels eternal, steady, untouchable. But if you listen closely, not with ears but with thought, you can sense a hidden director shaping the scene. It is gravity, the invisible hand not only pulling planets and galaxies into motion, but quietly editing the script of time itself. The idea that gravity could alter time was not obvious to the ancients. To them, gravity was the pull that caused apples to fall and moons to circle their planets. Time, by contrast, was an independent drumbeat, impartial and eternal, moving in lockstep everywhere. Isaac Newton himself assumed this, that time flowed equably without relation to anything external. For over 2 centuries that assumption held, but Einstein overturned it with a single stroke, showing that gravity does not merely shape space, it bends the flow of time. Here is the proven fact. Clocks run slower in stronger gravitational fields. This phenomenon, called gravitational time dilation, is not a metaphor. It has been tested, measured, confirmed. A clock at sea level ticks imperceptibly slower than a clock on a mountaintop. A GPS satellite high above Earth must correct for this effect to function, for its clocks run slightly faster than those on the ground. Without accounting for relativity, your phone's location would drift kilometers in a single day. The history of this realization begins with Mercury. Astronomers in the 19th century noticed something strange about its orbit. The innermost planet, racing so close to the Sun, did not return to the same position after each revolution. Its orbit precessed, shifting slightly each century in a way Newton's equations could not explain. To Bain Leverrier, the same astronomer who predicted Neptune, tried to solve the puzzle. Perhaps, he thought, another planet lurked closer to the Sun, tugging Mercury's path. He even gave it a name, Vulcan. But no Vulcan was ever found. The mystery endured until 1915, when Einstein unveiled general relativity. His equations showed that the Sun's immense gravity warps the space-time around it. Mercury, tracing that warped fabric, shifted just as observed. The anomaly was no flaw of Newton, no hidden planet. It was evidence that time and space themselves bend under gravity's hand. This warping is often explained through an image: a trampoline stretched taut, a heavy ball placed at its center. Smaller balls roll inward, tracing curves around the depression. It is a useful picture, but incomplete. For the true strangeness lies not only in space curving, but in time slowing. Imagine standing at the bottom of a deep well. Your clock ticks a little slower than the clock of someone standing at the top. Neither of you notice, for within your own frame, everything feels normal, but when you compare, you find your seconds stretched, your minutes elongated. Gravity has been editing your experience all along. Now comes the odd, the speculative. Could extreme gravity serve as a time machine? Near a black hole, the warping becomes so severe that time itself nearly halts compared to the universe outside. A traveler descending near the event horizon might experience hours while millennia pass beyond. In this way, gravity becomes a portal to the future, a one-way journey into what lies ahead. The movie Interstellar dramatized this, showing astronauts aging little while decades rushed by on Earth. Fiction, yes, but rooted in physics. The equations agree: the deeper you fall into gravity's grasp, the slower your time flows. But here lies the debate: is space-time geometry the ultimate description, or merely an approximation of deeper laws we have not yet glimpsed? Some physicists believe gravity itself may be emergent, not fundamental, but arising from quantum entanglement or thermodynamics. If true, then time dilation is not the bending of a fabric, but the shadow of some underlying principle. Others argue relativity is complete at large scales. Only when married to quantum theory will its true scope emerge. The argument continues, echoing in conferences, whispered in chalk dust across blackboards. To make this more tangible, imagine light climbing out of a gravitational well. As it struggles upward, its wavelength stretches, becoming redder, a phenomenon called gravitational redshift. Time dilation is its twin. Not only light, but clocks themselves stretch under gravity's pull. Astronomers have measured this redshift from white dwarfs, compact stars whose gravity is immense. In their light, you can see time itself, slowed and reddened by the grip of mass. The scale of these effects humbles the mind. At Earth's surface, the difference is slight, nanoseconds lost or gained. Yet even this matters in practice, for without it, our machines falter. On cosmic scales, the differences become profound. At the edge of a black hole, the stretching of time is so extreme that the concept of before and after nearly collapses. From afar, it appears the infalling traveler never quite crosses the horizon, frozen in time. From the traveler's view, the crossing happens swiftly, the rest of the universe racing ahead in a blur. Two perspectives, both true, stitched together by relativity. It is tempting to imagine using such extremes for exploration, to send a vessel near a black hole, let it drift, and return with knowledge from a far future. A shortcut, not to the past, but to the yet to be. Yet the dangers are immense. Tidal forces tearing apart matter, radiation searing from accretion disks. Gravity guards its secrets jealously. Still, in theory, such voyages mark one of the clearest, most physical ways to travel forward in time. And so, gravity becomes not merely the sculptor of galaxies, but the hidden editor of moments. Each star, each planet, each black hole bends not only space, but the rhythm of seconds. To live in this universe is to live in a fabric perpetually distorted, time itself woven into every contour of mass and energy. The silence of gravity deepens this strangeness. You cannot hear it. You cannot feel it except through weight, and yet it dictates not only your path through space, but the rate at which your heart beats against eternity. It is the clockmaker behind all clocks, unseen but absolute. As you drift in thought, imagine again the river of time. Now, see it not as level, but warped by unseen hands. Pools where it slows, cascades where it accelerates, whirlpools where it loops. Gravity is the artist of those shapes, turning a steady current into a restless terrain. From Mercury's orbit to GPS satellites, from white dwarfs to black holes, the evidence is undeniable. Time does not flow equally everywhere. It is bent, stretched, rewritten by mass. The river has an editor, and that editor is gravity. Ahead, we will follow this path deeper, into the experiments that prove these ideas beyond theory, into the mountains where moons fall, into the sky where astronauts' clocks diverge, into the very pulse of atoms that keeps track of time with impossible precision. But before we step there, let us pause with the wonder. The next time you feel the pull of gravity holding you to Earth, remember, it is not just pulling your body downward, it is tugging at your seconds, sculpting your minutes, stretching your hours. Gravity is not only the force that shapes space, it is the silent editor of time. High above the mountains, the air thins until your breath becomes shallow, your heartbeat deliberate. The horizon stretches, blue fading into black, and with each step upwards, something subtle happens. Time itself shifts. It ticks just a little differently here than it does below, as though altitude carries not only your body higher, but your seconds into a slightly faster current. This is no illusion, no quirk of imagination. It is a measurable fact, one proven by the most delicate of experiments and the most cosmic of particles. The story begins not with satellites or spacecraft, but with ghostly visitors from space, particles known as muons. They are born when cosmic rays strike the upper atmosphere, colliding with atoms and releasing showers of exotic fragments. Muons are unstable. Left alone, they decay quickly, with a half-life of just 1.56 millionths of a second. According to classical reasoning, most muons should vanish long before they reach the ground. Yet when scientists carried instruments to mountaintops in the mid-20th century, they found something astonishing. Far more muons survived the journey than Newtonian physics could explain. The Italian physicist Bruno Rossi and his colleagues performed one of the most elegant demonstrations of this phenomenon at Mount Evans in Colorado. At the mountain's summit, detectors registered a steady rain of muons. Descending towards sea level, Rossi expected to find a dramatic drop in their numbers. Instead, many of the muons had endured, seemingly outlasting their own brief lifespans. The explanation was hidden in Einstein's relativity. To the muons, racing close to the speed of light, time itself slowed, their internal clocks ticked sluggishly, granting them more moments to exist. Meanwhile, from our perspective on Earth, their journey was shortened by the compression of distance at such velocities. Two sides of the same coin, time dilation and length contraction. Here lies the scientific fact. Moving clocks run slow. Whether those clocks are delicate instruments or subatomic particles, relativity ensures that motion stretches their lifespans. The muon experiments proved this with extraordinary clarity, revealing time not as an absolute backdrop but as a participant in the dance of speed and space. Now imagine the speculative oddity. If you could ride alongside a muon, clinging to its quantum saddle as it hurtles through the atmosphere, you would find its lifetime unchanged. To you, it would still flicker out in just over a microsecond. But glancing back at Earth, you would see the planet blurred, distances shortened, landscapes crushed together like pages flipped too quickly. To the muon, it is not living longer, it is the universe that has conspired to shorten the road. This duality is one of relativity's strangest gifts. Reality is true from every perspective, even when perspectives contradict. The debate that lingers is not about whether time dilation exists. It is as solid as any law of physics. Instead, it is about its implications. Does this mean the future already exists, waiting for those who travel fast enough to meet it? Or is the passage itself what constructs reality, moment by moment? The block universe view, which we touched upon, insists that every future already lies written. Others suggest the future is only potential, shaped by choices and chance. Muons do not answer these questions. They only show that time is more flexible than we once believed. But particles are not the only clocks in this story. Human beings have become time travelers too, if only by fractions of seconds. Consider the twin paradox, one of relativity's most famous thought experiments. Imagine identical twins. One boards a spaceship, accelerates to near light speed, and travels among the stars. When she returns, she is younger than the sibling who stayed on Earth. It sounds like science fiction, but in practice, the principle has been tested in miniature. Astronauts orbiting Earth experience time differently than those on the ground. The American astronauts Mark and Scott Kelly, identical twins, provided a poignant example. Scott spent a total of 520 days in space, while Mark remained Earthbound with only 54 days aloft. When they reunited, careful measurements revealed a tiny but real difference. Scott had aged ever so slightly less than his brother. It was not 6 minutes, as simplified accounts once suggested, but milliseconds, yet measurable. The paradox had crossed from theory into lived experience. And then there are the machines we rely on every day, the satellites of the global positioning system. Each one carries atomic clocks, instruments so precise they can keep time within billionths of a second, but orbiting high above Earth, their clocks run faster than those on the surface. If engineers ignored relativity, GPS positions would drift by kilometers within a single day. To guide your steps across a city, to navigate a ship across oceans, requires acknowledging Einstein's strange truth. Time itself bends differently depending on where you stand, how you move, how deep you sit in Earth's gravity. Every time you check a map on your phone, you are witnessing relativity in action. To visualize this, think of two climbers on a mountain. One remains near the base, the other at the summit. Each carries a clock. To their eyes, both clocks tick normally, but when they reunite, the summit clock has marched ever so slightly ahead. The difference is imperceptible without sensitive equipment, but it is there, and it grows with altitude. Time is not equal, it is local. In recent years, experiments with optical lattice atomic clocks have sharpened this truth even further. In 2022, researchers demonstrated time dilation across distances smaller than the thickness of a human hair. Two clocks, placed millimeters apart, one slightly higher than the other, ticked at different rates. The effect was not theoretical. It was observed, measured, undeniable. Imagine, even the act of lifting your head causes the clock in your brain to run a fraction faster than the clock in your feet. We live in a world of countless tiny time zones, each defined by position and motion. This revelation is at once thrilling and unsettling. Thrilling because it means time is pliable, a fabric stretched and twisted by nature itself. Unsettling because it undermines the certainty we crave. You think of time as shared, as collective, that the moment you live now is the same moment felt by every other soul, but relativity says otherwise. Each of us rides our own current, drifting at speeds and altitudes that subtly shift our experience of duration. The sky itself becomes a theatre of clocks. Muons streak downward, their decay slowed by motion. Satellites circle overhead, their seconds racing compared to hours. Astronauts drift in orbit, their lifespans stretched just enough to prove a point. And on Earth, our feet and heads live in slightly different temporal worlds. To live beneath this sky is to live in a universe where time is not fixed, but ever so gently fluid. Close your eyes and picture yourself lying in a field at night. The stars wheel above. You feel still, grounded. Yet within you, muons are born and die. Particles blink into being and out again. Overhead, invisible satellites trace their courses, each one correcting its seconds against Earth. Far beyond, astronauts glide in a slower stream. It is all happening at once. Time, fractured into countless streams, stitched together only by perception. From the mountain summits to the edge of orbit, the evidence is clear. Relativity is not confined to textbooks. It is written into the sky, into the particles that rain upon us, into the machines that guide us home. When you lift your eyes upward, you are not only seeing space, you are seeing the very laboratory where time itself reveals its pliability. And so the river of time grows stranger still. No longer does it flow evenly, but in eddies and currents, fast in one place, slow in another. In the sky above, the clocks that measure this flow tick at different rhythms, each telling a slightly different story of the same universe. To walk upon Earth, to gaze at stars, is to walk within a garden of uneven seconds. Ahead lies an even more delicate exploration, the pulse of atoms themselves, and how we have harnessed them to measure time with a precision that borders on the miraculous. But here, among the muons and satellites, the lesson is already profound. Time is not universal. It is local, personal, sculpted by motion and gravity. And once you know this, the notion of traveling through time is no longer a dream. It is, in some sense, already happening all around you. In a quiet laboratory, far from the tumult of stars and black holes, The secret rhythm of the universe is captured in the trembling of atoms, not the ticking of gears or the swing of pendulums, but vibrations deep within the heart of matter. These are the atomic clocks, guardians of precision, whose steady beats measure time with such fidelity that they redefine what it means to know a second. If the muons in the sky revealed the pliability of time, then atomic clocks gave us the means to measure that pliability with impossible accuracy. Timekeeping has always been more than convenience. It was once the rhythm of agriculture, the turning of seasons marked by solstices and shadows. It became navigation, sailors charting oceans by the angle of the sun. It became civilization itself, synchronized by bells and calendars. Yet none of these compare to the leap achieved when scientists harnessed the oscillations of atoms. In 1967, the International System of Units defined the second, not by Earth's rotation, but by the natural vibration of cesium-133 atoms. 1 second equals 9,192,631,770 oscillations of that atom's radiation, a number unimaginably vast, yet perfectly repeatable. The pulse of the atom replaced the turning of the Earth. Here lies a fact, both beautiful and strange. The best atomic clocks lose or gain less than 1 second over the age of the universe. Modern versions, optical lattice clocks, achieve accuracies of 15 billionths of a second per year. These instruments do not simply mark time, they carve it with surgical precision. They allow GPS satellites to function, deep space missions to navigate, and experiments to reveal the subtle warping of space-time itself. Now imagine the oddity: two such clocks, placed mere millimeters apart, begin to disagree. In 2022, researchers demonstrated this with breathtaking clarity. By elevating one clock slightly above the other, they observed time dilation across the tiniest vertical difference. Gravity, weak as it is near Earth's surface, still tugged at time, pulling it slower in the lower clock. The difference was unimaginably small, yet measurable. To lift your head is to move into a subtly different temporal stream than your feet. The fabric of time is not uniform even across the span of your own body. But here is the open debate. What, truly, are these clocks measuring? Are they capturing an external flow of time, a river outside ourselves? Or are they simply cataloguing the unfolding of physical processes, no more fundamental than the ticks of a pendulum? Some physicists argue time itself may be emergent, not fundamental, arising from deeper quantum phenomena. If that is true, then atomic clocks are not measuring an independent river at all. They are tracking the harmonies of the universe's own music, harmonies that only appear as time when we listen from within. Imagine standing in a great hall where countless violins play. Each one represents an atom, vibrating with precision. Together they create a cosmic symphony. The clocks do not invent the rhythm, they reveal it, count it, synchronize to it. Yet the symphony may be an illusion of scale, an emergent melody woven from deeper silence. The truth may lie beyond even the most perfect clock. Still, their power is undeniable. Without atomic clocks, GPS satellites would fail in hours. Each orbit alters their rhythm, requiring constant corrections for both speed and gravity. Relativity is not an abstraction for them, it is their operating condition. When your phone guides you through a city street, it relies on the corrections of Einstein's equations applied to cesium's vibrations. Every step you take, every route you map, is built upon relativity, harnessed in the pulse of atoms. And beyond navigation lies the frontier of discovery. Physicists use atomic clocks to test whether the constants of nature, the speed of light, the strength of forces, remain the same across time and space. If the universe's laws drift even slightly, atomic clocks will reveal it. In this way, timekeeping becomes cosmology, the pulse of atoms whispering secrets about the stability of the cosmos itself. Think of the human heartbeat. It is steady, reassuring, the rhythm of life itself. Atomic clocks are the heartbeat of the universe, so regular they redefine certainty. Yet even they are not immune to the stretching hand of relativity. Raise a clock into orbit, and it races ahead. Place it at the edge of a black hole, and it slows to near stillness. No matter how perfect the mechanism, time itself bends beneath the fabric it inhabits. Speculation follows. What if we could string a network of such clocks across the galaxy, comparing their pulses in different gravitational wells at different speeds in the vicinity of strange objects? The differences would not only confirm relativity, but could reveal new physics, cracks in the theory, hints of a deeper law. Some dream of detecting dark matter or dark energy through their faint fingerprints on time's flow, caught not by telescopes but by clocks. And so the atomic clock becomes more than a tool. It is a lens, showing us that even the smallest shift in position creates a new tempo. Your life is lived not in one universal time, but in 1,000 overlapping timescales, stitched together only by perception. The pulse of atoms reveals this with a certainty that humbles imagination. Close your eyes and listen, not to silence but to vibration. Deep within you, atoms quiver at frequencies that make no sound, yet form the metronome of existence. Around the world, laboratories cradle clocks so sensitive they measure the imperceptible tilt of Earth's crust, the tug of tides, even the heartbeat of the planet itself. To live in this age is to dwell in a universe where time is mapped not by the sun or the moon, but by the secret rhythm of matter. And yet, for all their precision, the mystery remains. Are we measuring something real, or constructing meaning from oscillation? Is the universe itself keeping time, or are we the ones inscribing a beat onto its silence? The debate stretches on, unanswered. The pulse of atoms is certain, but the essence of time remains elusive. Still, we follow the beat. The moons in the sky hinted that motion bends time. The satellites above confirmed it. The twins, the astronauts, the experiments, they all converge on this truth. Time is pliable, and the atomic clocks with their perfect pulses are our witnesses. They prove that the universe is stranger than Newton ever dreamed, stranger than common sense dares to believe. Now, as we leave the quiet hum of the laboratory, our gaze turns once more to the cosmos. For not all discoveries come from precision and silence. Some arrive as shouts, as false alarms, as bold claims that crumble under scrutiny. Ahead lies such a tale, a story of particles that once seemed to outrun light itself, threatening to overturn Einstein, only to reveal the humility at the heart of science. The pulse of atoms has prepared us, showing how carefully time must be measured. What comes next is a reminder that even in the age of precision we can stumble, and that from those stumbles, new questions rise. In the autumn of 2011, a rumor spread through the halls of physics that seemed almost impossible to believe. From the depths of the Gran Sasso laboratory in Italy, buried beneath mountains to shield it from cosmic noise, came whispers that a beam of ghostly particles had done the unthinkable. Neutrinos, those nearly massless phantoms born in the heart of stars and nuclear reactions, appeared to have outrun light itself. If true, it would not only upend Einstein's relativity, but tear open the door to a new understanding of time, perhaps even backward travel through it. The experiment was known as Opera. Scientists fired a stream of neutrinos from CERN in Geneva, letting them pass invisibly through the crust of the Earth to detectors in Italy. Some 730 kilometers away, the timing was exquisitely measured, synchronized with atomic clocks, but the result shocked them. The neutrinos seemed to arrive 60 nanoseconds early, as though they had traveled faster than light. For months, the physics community reeled. Could this be real? If nothing moves faster than light, then the speed of light is the ultimate cosmic speed limit. Break it, and causality itself begins to crumble. Events could reverse. Effects could precede causes. Paradoxes would no longer be speculation, but physics. Here lies the hard fact. If particles can truly surpass light, then time itself becomes malleable in ways we are unprepared to understand. Relativity tells us that faster-than-light motion would flip the order of events, allowing messages to be received before they were sent, or travelers to arrive before they departed. It is a terrifyingly unstable proposition, one that Einstein himself argued the universe would never permit. But here lies the oddity. The opera claims seemed, at least briefly, to suggest just such a breach. Media outlets ran breathless headlines about the end of physics as we know it. Some scientists dared to whisper that maybe, just maybe, the door to time travel had cracked open. The world waited for confirmation. And here lies the open debate. Could nature permit faster-than-light travel at all? The neutrino, elusive and enigmatic, has always been a source of mystery. For decades, physicists believed it was massless. Only recently did experiments confirm it has a tiny but non-zero mass, forcing revisions to the standard model. If neutrinos held other surprises, if they could somehow tunnel through space-time shortcuts, then perhaps Einstein's limit was not as unbreakable as once thought. But if they did not, then opera's results were merely a cautionary tale about measurement and humility. As history records, the latter proved true. Months of scrutiny revealed that a loose fiber optic cable and a faulty oscillator had skewed the timing system. The neutrinos had never broken light's barrier. The anomaly was man-made, not cosmic. The discovery was not revolution, but correction. And yet, the episode remains one of the most haunting in modern science, a brief moment when the impossible seemed to have breached the walls of certainty. To feel the drama of that moment, imagine standing in the control room as the first results came in. Screens flicker with lines of data, clocks synchronize across borders, pulses of neutrinos vanish into the earth. Then, the numbers whisper something forbidden. You check again, and again, always the same. The neutrinos are early. The pit of your stomach sinks. If true, the foundations of physics tremble. But if wrong, your career, your credibility, perhaps even your sanity, could be at stake. The room holds its breath. The episode echoes older lessons. Science advances not through certainty, but through doubt, through claims tested, until only truth survives. The neutrinos of opera did not rewrite relativity, but they sharpened it. They reminded us how fragile measurements can be, how vigilant we must remain. Even error handled properly illuminates. Speculate, though, for a moment. What if the neutrinos had truly broken light's barrier? Imagine particles routinely slipping backward through time, leaving trails in detectors that do not begin where they should. Imagine messages encoded in beams of tachyon-like particles, arriving before they are sent. Civilizations could, in principle, relay warnings to their own pasts, reshaping history before it unfolds. Yet such a world would be unstable, riddled with paradoxes. The bootstrap, the grandfather, all would become living realities. Some physicists believe that is precisely why the universe forbids faster-than-light motion, because it would tear the coherence of causality itself. And yet, the debate remains unresolved. There are frameworks in theoretical physics, quantum field theories with exotic solutions, speculations about wormholes or entangled particles, where faster-than-light correlations appear, if not signals themselves. The universe flirts with the forbidden, offering hints without clarity. Einstein's limit has held firm, but the hunger to test it never fades. Think of neutrinos themselves. They pass through you by the trillions every second, born from the nuclear furnace of the sun. They barely notice you, barely notice Earth itself. They are messengers of the cosmos, whispering secrets across unimaginable distances. To chase their shadows is to pursue the edges of possibility. They remind us that most of the universe is invisible, hidden beneath surfaces we barely comprehend. In the opera hall, beneath kilometers of rock, detectors wait in silence. Photomultiplier tubes glow faintly, recording rare flashes of interaction. Outside, mountains rise, seasons turn. Yet below, the hunt for neutrinos continues. The failed claim of faster-than-light travel does not end the story. It only deepens it. Each neutrino captured is another brushstroke on the canvas of time, another clue to how the universe guards its secrets. For in the end, what opera truly revealed was not the failure of relativity, but the resilience of science. Mistakes are not ends, they are waypoints, reminding us that humility must stand beside ambition. To chase the shadows of neutrinos is to chase whispers of reality itself. Sometimes they lead us astray, sometimes they lead us deeper. Always, they remind us how much we do not yet know. And so we leave Gran Sasso, not with the certainty of time travel achieved, but with the sharpened wonder that such possibilities are even thinkable. The neutrinos remain elusive, their shadows long. They have not cracked open time's door, but they have shown us where the hinges might be. Ahead lies not rumour but theory made vivid, cylinders spinning through infinity, geometries twisting space-time into loops. The chase continues, now with equations and imagination side by side. For if neutrinos cannot deliver us backward, perhaps other paths remain. Picture the universe as a tapestry stretched beyond sight, its threads woven not only of matter but of space and time themselves. Now imagine taking that fabric and twisting it, rolling it into a colossal spindle that spins without end. This is not a dream or a myth, but a mathematical vision born in the minds of physicists. It is the idea of a cylinder so immense, so perfect in its symmetry, that its endless rotation might create closed loops in space-time, paths that curve back upon themselves, allowing a traveller to step into the past. The seed of this idea was planted in 1937, when mathematician Willem Jacob van Stockham discovered a peculiar solution to Einstein's equations of general relativity. He imagined a universe filled with an infinitely long cylinder of rotating dust. In this strange cosmos, space-time did not merely curve, it twisted. Around the cylinder, the geometry of reality bent in such a way that closed time-like curves appeared, pathways through the fabric where an object could travel forward in time, only to loop back to its own past. Later, in 1974, the American physicist Frank J. Tipler carried this vision further. He proposed what became known as the Tipler cylinder, an infinite, massive cylinder, rotating at nearly the speed of light. Such an object, in theory, would warp space-time into a spiral, opening corridors where cause and effect no longer marched strictly forward. A spacecraft circling the cylinder in just the right path could, according to the equations, arrive in its own history. Here lies the scientific fact. Einstein's field equations permit such exotic solutions. The mathematics is sound. Within the framework of relativity, space-time can indeed twist into loops. General relativity does not forbid time travel. It sketches blueprints for it, hidden in the elegance of its geometry. Yet here lies the oddity. These solutions demand conditions that border on the impossible. A cylinder of infinite length cannot exist in our finite universe. Even if one did, the energy required to spin it at near-light speeds would be astronomical. The very concept stretches practicality beyond the breaking point. Still, the idea persists in the imagination, because it proves something profound. The laws of physics, at least on paper, do not seal time's door shut. And here lies the debate. Are such mathematical solutions glimpses of reality, or are they artifacts, tricks of equations that cannot survive the messy complexity of the real cosmos? Some physicists argue that infinite cylinders and closed time-like curves are fantasies, forbidden not by mathematics but by physical constraints. Others suggest that even if such objects cannot exist in our universe, they reveal hidden principles, that the fabric of space-time contains, at its edges, possibilities far stranger than anything we've yet built. To make this vivid, imagine standing beside such a cylinder. It stretches beyond sight, vanishing into the heavens, its surface shimmering with impossible velocity. Space around it is no longer straight but twisted, like water spiraling down a drain. As you step closer, your sense of direction falters. Forward feels sideways, sideways feels back. Then, as you follow a loop around the cylinder, You find yourself emerging not ahead but behind, not in the future but in the past. The world around you is the same, yet younger. The paradoxes stir. Have you altered history, or only joined a loop that was always there? Speculation grows wilder. Could a civilization of unimaginable power create such an object? Perhaps not infinite, but large enough, dense enough, fast enough to approximate the effect. Some theorists suggest that cosmic strings, one-dimensional defects from the early universe, might mimic the geometry of a tipless cylinder, providing a natural analogue. If so, the cylinder is not fantasy, but cousin to structures that might have truly been woven into space-time in its infancy. Still, doubts remain. Stephen Hawking, ever skeptical of time machines, invoked his chronology protection conjecture, suggesting the universe conspires to prevent closed time-like curves from forming. Quantum effects, he argued, might destabilize any attempt, flooding it with energy until the geometry collapses. If Hawking is right, then the infinite cylinder is a mirage, a solution forbidden by the deeper laws of physics. But if he is wrong, then the blueprint still beckons. The cylinder embodies both promise and impossibility. On one hand, it is a vision that shows time's rigidity is not absolute. On the other, it demands infinities no universe can provide. The paradox is almost poetic. The key to the past lies in an object that cannot exist, a path forever visible in theory yet unreachable in practice. And yet, the power of the infinite cylinder is not diminished by its impracticality, like the parabola in mathematics. Perfect and endless though never realized in matter, it guides thought, shapes imagination, sets boundaries on what might be possible. It teaches us that time itself is not sacred, not inviolate. It can be twisted, looped, bent into shapes that defy intuition. Close your eyes and feel the image. A spindle turning forever, its hum resonating, not in air but in space-time itself. Around it, moments curl back, braiding yesterday into tomorrow. Travelers loop endlessly, chasing their own shadows. Somewhere within those spirals lies the answer to the paradoxes. If time can loop, then perhaps cause and effect are not destroyed, but rewritten into cycles we do not yet understand. And so the infinite cylinder stands, not in the cosmos, but in the mind, a reminder that our equations can lead us to landscapes where time folds back on itself. It is not proof of possibility, but it is proof of imagination made rigorous, of speculation anchored in mathematics. As we step away from its impossible surface, the question remains, if cylinders cannot carry us backward, might other geometries succeed? Perhaps not endless spindles, but tunnels, wormholes threading through space-time, bridges from here to there, now to then. If the cylinder was the first bold dream of relativity, wormholes are the dream's continuation, gateways, not infinite but finite, sculpted into possibility. And it is there, in those tunnels, that the imagination of science takes its next leap. Imagine holding a sheet of paper. At one edge you draw a dot, the present. At the opposite side, another dot, the future, or perhaps the distant past. Normally, you trace the line across, patient, steady, but if you fold the paper until the dots touch, the path collapses. The distance, once vast, is now a breath. This is the essence of the wormhole, a tunnel through space-time that bridges what would otherwise be unimaginably far, or separated by centuries, or even eons. The concept is not the invention of science fiction, though stories have seized it with fervor. It arises directly from Einstein's field equations. In 1935, Einstein and his collaborator Nathan Rosen discovered a solution now called the Einstein-Rosen bridge. They imagined space-time not as flat and smooth, but as a manifold that could fold, allowing shortcuts. At first they pictured it as a bridge connecting two black holes, a tunnel whose ends opened into distant places, but the equations whispered something even stranger. Perhaps such bridges could connect not only places but times. Here lies the scientific fact. General relativity does not forbid wormholes. In fact, its equations suggest they can exist. The trouble is stability. The original Einstein-Rosen bridges collapsed too quickly for anything, even light, to cross. They snapped shut like soap bubbles. For decades, wormholes remained a tantalizing mirage, mathematically possible, but physically unreachable. And then, in 1985, fiction catalyzed reality. The astronomer Carl Sagan, writing his novel Contact, wanted a scientifically plausible way for his characters to traverse the galaxy. He consulted physicist Kip Thorne. Could relativity permit such a journey? Thorne, intrigued, set his students the task. The result was a groundbreaking paper. Yes, wormholes might be traversable if held open by something exotic, something beyond ordinary matter. Here lies the oddity. To stabilize a wormhole, one must use negative energy. Unlike ordinary energy, which attracts, negative energy repels, pushing space-time outward. In principle, it could prop open the tunnel, preventing collapse. Such energy is not fantasy. In the quantum vacuum, fleeting fluctuations create pairs of particles and antiparticles, a dance of creation and annihilation that briefly dips into negative values. Physicists have glimpsed this in the Casimir effect, where two plates placed close together experience a strange force from suppressed vacuum fluctuations. Could this same quantum oddity serve as the scaffolding for a wormhole? Here lies the debate. Is negative energy a usable resource, or merely a mathematical curiosity? Some argue the amounts required to stabilize a wormhole, large enough for human passage, would be astronomical, far beyond anything nature provides. Others speculate that in the early universe, where energy densities were extreme, wormholes may have formed naturally, relics scattered across the cosmos. If so, they might still exist, hidden in the void, silent shortcuts waiting to be found. To envision a wormhole, picture a sphere in space, shimmering like heat haze. Step closer and the stars behind it distort, bent by the gravitational lensing of the tunnel's mouth. To cross its threshold is to feel no shock, no jolt, but a seamless passage. One step, and you are light years away. One heartbeat and centuries have passed. Inside, the tunnel walls glow faintly with the tension of curved space-time, as though the cosmos itself strains to allow the passage. Speculation grows bolder. What if wormholes could be engineered? A civilization advanced enough might sculpt space-time, as easily as we sculpt clay, threading tunnels across galaxies, braiding errors together. Time travel, in this vision, is no longer myth but infrastructure, the architecture of a cosmic highway. One could leave Earth in the 21st century and arrive in its 31st, not by waiting but by stepping. And yet the paradoxes stir. Suppose you pass through a wormhole that links 2025 to 2125. You emerge a century ahead. If the other mouth remains near Earth while one is accelerated close to light speed and returned, relativity ensures their times diverge. Reconnect them, and you have a time machine. Enter one mouth and step not into elsewhere but into elsewhen. Cause and effect begin to blur. Paradoxes rise like mist. Could you meet yourself? Could you prevent your own crossing? Would history splinter or bend to consistency? Hawking's chronology protection conjecture hovers here like a guardian. Perhaps, he argued, wormholes that permit time travel would self-destruct under quantum effects, flooded with energy until they collapse. Others countered with models showing stability under certain conditions. The debate rages in the borderlands of theory, where equations stretch into the unknown. The imagery remains irresistible. A starship circling the void, sensors flickering as a distortion blooms, a sphere dark at its edges, luminous within. The ship drifts closer, swallowed by the tunnel. Outside, centuries roll on. Inside, only moments pass. When the vessel emerges, history has changed. And here lies the speculative oddity. Some suggest black holes themselves might hide wormholes at their cores. Instead of singularities, points of infinite density, perhaps they conceal tunnels to other universes, other timelines. If so, the countless black holes scattered through galaxies are not tombs but gateways, locked, silent, awaiting keys we do not yet possess. Even stranger, entanglement in quantum physics, the ghostly correlation between particles no matter the distance, has been proposed as a kind of wormhole. Some physicists, in a bold conjecture, suggest that entangled particles are connected by microscopic bridges of space-time, invisible wormholes threading the quantum foam. If true, then wormholes are not exotic rarities, but the very fabric of entanglement itself, woven into every corner of reality. Yet for now, they remain speculation, glimpsed only in equations and imagination. No telescope has ever seen one, no experiment has proved their stability, and still they linger at the edge of possibility, beckoning. Close your eyes. Imagine stepping into a garden where every archway is a wormhole, each opening onto a different landscape. A frozen tundra under alien stars, a city yet to be built, the same place centuries ago. Each passage invites, each path dares. Behind them all lies the same question: is time truly unidirectional, or is it merely our minds that move forward, while the cosmos holds all directions open? The wormhole is not yet real, but it is a reminder that time travel is not merely fantasy. It is a problem of engineering, of energy, of stability. Nature does not forbid it outright. It whispers through equations that shortcuts exist. Whether we can ever use them remains unknown. As we leave these tunnels of possibility, the fabric of space-time still hums with tension. Cylinders twisted into infinity, wormholes threading across universes, both show that time is pliable in theory. But perhaps the universe has even stranger scars. Not tunnels, not spindles, but threads. Cosmic strings, remnants from creation itself, stretching across the cosmos, their tension enough to bend time's arrow. And it is toward those threads that we now turn. Imagine standing at the dawn of the universe, when everything was new and unimaginably dense. The cosmos had just erupted from the Big Bang, a searing ocean of particles, radiation, and energy tangled together in chaos. As it expanded and cooled, the newborn fabric of space-time may have shivered and cracked, leaving behind scars, not scars of matter, but of geometry itself. These are the cosmic strings, hypothetical relics of creation, infinitely thin filaments stretching across the cosmos, taut with tension so great that they could bend light, warp space, and perhaps even open corridors through time. The idea was first proposed in the 1970s and 1980s, when physicists explored how symmetry might have broken in the universe's earliest moments. Just as ice freezes with cracks and defects, so too might space-time have crystallized with imperfections. These defects, if real, would not be ordinary matter, but structures baked into the very equations of the cosmos. Unlike stars or planets, they would have no thickness in the ordinary sense, narrower than a proton, yet longer than galaxies. Here lies the scientific fact. General relativity predicts that objects of immense density and perfect linear form would warp space-time in strange ways. A cosmic string, though thinner than imagination, could carry as much mass per unit length as a mountain compressed into a hair's breadth. The gravitational field around it would not curve like that of a planet, but create a wedge-shaped distortion, cutting and rejoining space like scissors through cloth. Light passing near it would split, producing distinctive lensing patterns. Astronomers have searched the skies for these signatures, scanning for doubled or distorted images of galaxies that could betray the presence of strings. So far, none have been confirmed, yet the possibility lingers. Now here lies the oddity. If two cosmic strings passed close by one another, their combined motion could in theory create closed time-like curves, pathways through space-time that loop back upon themselves. This was shown by physicists J. Richard Gott and William Hiscock in the 1990s. Imagine two strings racing past one another at nearly the speed of light. The distortion of space-time around them could be so severe that a spacecraft threading between them might emerge not ahead but behind in its own past. The equations allow it. The paradoxes awaken. And here lies the debate. Do cosmic strings exist at all? Some versions of string theory predict them. Others dismiss them. Observational searches have yet to find definitive proof. The cosmic microwave background, the afterglow of the Big Bang, has been combed for their fingerprints, but none stand beyond doubt. Critics argue that the lack of evidence suggests strings are either too rare or too subtle to detect. Believers counter that the cosmos is vast, and what has not yet been seen may still lie hidden. To feel their presence, imagine a thread stretched across the night sky. It is invisible, silent, thinner than thought. Yet as you watch, stars near it shimmer strangely, their light bent as if reflected in water. The thread hums with unimaginable energy, its tension equal to the strength needed to split the universe itself. Were you to pluck it, its vibration could ripple through space-time, a wave of gravity felt across galaxies. Speculation takes us further. Suppose a civilization discovered a cosmic string, or even learned to weave them. Could they harness its tension, shaping closed loops of time? Could they lace space-time with paths to the past, constructing not tunnels but threads that stitch eras together? Some imagine networks of strings forming cosmic fabrics, where time itself becomes a weave. Others warn that such power would be catastrophic, for the energy of a single string could unravel worlds if disturbed. Consider the image of two strings nearly colliding. Their passage would send gravitational waves rippling outward, shaking space-time itself. If those waves intersected just right, they might open pockets where time folds back, loops nested within loops. A spacecraft daring enough to dive through might slip into yesterday or into a tomorrow already past. But even here, caution reigns. Hawking's chronology protection suggests that quantum effects would destabilize such loops, preventing usable time machines. Vacuum fluctuations might swell uncontrollably near the strings, blasting the corridor apart before anyone could cross. Once again, the universe seems to guard its consistency jealously. Still, the allure remains. Cosmic strings are not merely fantasies. They are predictions drawn from real mathematics, from attempts to unify the laws of nature. Their existence would reveal truths about the early universe, about how forces split and symmetries broke. If found, they would be relics older than stars, fossils from the first instant of time. And if harnessed, they could be keys not only to energy beyond measure, but to the very architecture of history. Picture walking through a forest at twilight, threads of spider silk stretching between branches, invisible until caught by the light. Each string glimmers briefly, delicate yet strong enough to hold a web. Cosmic strings would be the universe's own silk, invisible until they bend light, yet strong enough to reshape entire epochs. They may not be everywhere, but they could be anywhere, silent threads stretched across the void. And here lies another speculative oddity. If strings do exist, they may not be infinite. They could form loops, circles snapping across space at near-light speed. These loops would vibrate, radiating gravitational waves. Some might collapse in bursts of energy, others might persist, oscillating for billions of years. Could such loops, if dense enough, create localized distortions of time? Could they serve as natural laboratories for paradox? The math hints, though the answers remain unfinished. The debate intensifies when linked with quantum theory. Some physicists suggest that if space-time itself is granular, composed of quantum bits of geometry, then cosmic strings might be the edges of that weave, where patches of reality fail to align. If so, they are not anomalies but necessities, the stitches in the universe's quilt. Others reject this, arguing that cosmic inflation would have stretched or erased them long ago. For now, the evidence is absence. No telescope has yet caught a string in its net. but searches continue. Gravitational wave observatories like IGO and Virgo listen for their echoes. Astronomical surveys scan the heavens for doubled galaxies split by invisible wedges. Each failure narrows the hunt, but does not end it. Close your eyes and imagine a night sky threaded with hidden lines, a secret geometry laced through the stars. Somewhere out there, a string may hum, a remnant of the cosmos's birth, holding within it the possibility of bending not only space but time. To discover one would be to hold in our hands the threads of creation itself. As we leave these imagined filaments, the question sharpens: if cylinders twist time and wormholes tunnel it, and strings might weave it, then what of the quantum foam itself? At scales smaller than atoms, smaller than strings, the universe seethes with uncertainty. There, in the restless shimmer of nothingness, may lie the strangest key of all: negative energy, virtual particles, and the gamble of quantum time. Beneath the familiar world of stars and planets, beneath even the atoms that form your breath, lies a realm where certainty dissolves into possibility. It is the quantum domain, a place where particles flicker in and out of existence, where emptiness itself is restless, and where the laws of cause and effect bend under strange new rules. If time travel has any hope of escaping paradox and impossibility, many physicists believe the answer must live here, in the seething sea of the quantum vacuum. To grasp this, first imagine empty space. To your eyes, it is nothing. Black, silent, void. But to quantum physics, it is anything but empty. Even in perfect vacuum, particles and antiparticles are born in pairs, exist for fractions of moments, and then annihilate back into nothingness. This ceaseless flicker is called quantum fluctuations, and it means that the vacuum itself is alive. In 1948, Hendrik Casimir predicted, and experiments later confirmed, that these fluctuations can exert real forces. The Casimir effect: place two metal plates very close together, and the vacuum between them shifts. A force pushes the plates inward as though the nothingness itself had weight. Here lies the fact: negative energy is real. The Casimir effect shows that under special conditions, energy in a region of space can dip below what we consider normal. For wormholes, for closed time-like curves, for the stabilization of exotic geometries, such negative energy is the holy grail. With it, space-time might be propped open, curved or shielded in ways otherwise impossible. Without it, wormholes collapse, strings snap, and time machines implode. Now here lies the oddity. Negative energy is not easy to gather. The quantum vacuum offers it in fleeting, localized doses, whispers rather than shouts. No experiment has ever harnessed it in amounts sufficient to hold open a tunnel through space-time. Yet some theorists argue that with clever arrangements, perhaps involving intense lasers, magnetic fields, or the manipulation of quantum fields, we might amplify these effects. Others speculate that nature itself may already do so, in phenomena like Hawking radiation around black holes. And here lies the debate: is negative energy merely a curiosity or a usable resource? Some physicists, like Kip Thorne and his collaborators, take the equations seriously. If negative energy can be engineered, traversable wormholes might move from speculation to construction. Others insist the universe will not allow it. They argue that quantum inequalities prevent negative energy from being sustained or scaled, that every pocket of it must be balanced by larger regions of positive energy, preserving cosmic consistency. To feel this paradox, picture the quantum vacuum as a restless ocean at night. Small waves ripple and vanish. Fish leap briefly above the surface before diving back. Occasionally, a trough dips lower than the calm line, as though the ocean itself sagged. That sag is negative energy. To navigate time, one must ride these dips, capturing them before they vanish. But can we build ships to sail seas that vanish faster than thought? Speculation abounds. Some suggest negative energy could create warp bubbles, compressing space-time ahead of a spacecraft while expanding it behind, allowing effective faster-than-light motion without violating relativity. The Alcubierre drive, proposed in 1994, is one such concept, a bubble of curved space-time carrying a ship forward. At its heart lies the same requirement: negative energy in vast amounts. The equations work, the engineering does not. For now, it remains a dream carved in mathematics. Others stretch further still. Perhaps quantum mechanics itself, with its uncertainty and probabilities, prevents paradoxes not by forbidding time travel, but by allowing branching outcomes. In this vision, negative energy stabilizes the passage, while quantum theory ensures consistency. Travel into the past does not erase the present. It spawns a parallel timeline, a new branch of the wave function. The universe gambles, but never loses. The imagery here is rich. Imagine stepping into a chamber, walls humming with energy drawn from the quantum vacuum. The air seems to shimmer, as though the room were underwater. At the center, a tunnel opens, not fiery, not violent, but silent, calm, edged with faint light. You step forward, and in that step, you cross not only space but history. Yet as you emerge, you find the world unchanged. It is not your own past you have entered, but a twin, a branch, a reflection. In this way, the quantum gamble protects consistency. Paradox dissolves, not by denial but by proliferation. And here lies another debate. Does the universe truly branch as the many worlds interpretation suggests, or does it enforce self-consistency, as the Novikov principle insists, ensuring that any time traveler's actions were always part of history? The quantum gamble divides physicists, some seeing it as salvation, others as speculation without evidence. But even without branching, quantum mechanics reshapes how we think about time. In 2020, researchers in Australia and Canada proposed thought experiments showing that quantum systems interacting with their own pasts could avoid paradoxes. The mathematics revealed consistency emerging from uncertainty, as though probability itself was the guardian of causality. A traveler sending a particle back might change its state, but not in ways that broke logic. Instead, the past adjusted, weaving new coherence. This is the gamble, that uncertainty is not weakness, but strength, that the universe's refusal to provide definite outcomes is the very reason it can tolerate loops, echoes, and returns. Certainty would break under paradox. Probability bends. Imagine the quantum vacuum again, now not as ocean but as storm. Flashes of light burst and vanish. Particles flare like fireflies in darkness. Each flicker is a roll of dice, a gamble of existence. If time machines exist, they are not built in steel and glass alone, but in the dice rolls of the quantum world, each throw ensuring that paradox never triumphs. And yet, for all the promise, the quantum gamble remains hidden. No experiment has yet bent time with negative energy. No laboratory has yet created a wormhole or warp bubble. What we have are hints the Casimir plates nudged together, the Hawking radiation leaking from black holes, the mathematics that shows pathways but no bridges. Still, the very fact that physics does not forbid these dreams is extraordinary. Time, once thought rigid and absolute, now shimmers with possibility. Gravity stretches it. Motion bends it. Quantum mechanics whispers that even its paradoxes may be survivable. Each layer adds, not denial, but invitation. Close your eyes and listen to the hum of the vacuum, the silent thrum of existence, where nothing is ever truly empty. The gamble of the quantum world is that from uncertainty comes resilience, from flicker comes possibility. If time travel is ever to be real, it will not be through brute force, but through this delicate dance, harnessing the whispers of nothingness, the negative pulses of creation itself. From here, the journey turns to the paradoxes themselves, seen not as barriers but as riddles. Schrödinger's cat, alive and dead, trapped in a loop, becomes a mirror for timelines. Quantum mechanics does not silence these riddles. It amplifies them, offering solutions stranger than fiction. The gamble continues, from particles to paradox, from uncertainty to multiverse. And it is there, in the cat's quiet box, that we will next peer into the heart of time's strangeness. Somewhere in the quiet of imagination, a box sits sealed. Inside, a cat waits, neither alive nor dead, suspended in a haze of probability. This thought experiment, conceived by Erwin Schrödinger in 1935, was not about cats at all, but about the unsettling rules of quantum mechanics. The cat is both living and gone until the box is opened. Observation collapses the uncertainty into one reality. Until then, possibility itself is what exists. This paradox is often invoked to describe the strangeness of the quantum world, but it also whispers something about time. If the past can be revisited, or if loops can be formed, then the universe may resemble Schrödinger's box, multiple outcomes held at once, resolved only when experienced. Could this be how time travel avoids contradiction, not by forbidding paradoxes, but by allowing all possibilities to exist until one is chosen, or until many are allowed to branch? Here lies the scientific fact. Quantum mechanics is probabilistic. Electrons do not orbit as planets do, but spread as clouds of likelihood. Only when measured do they appear as particles in one place. This has been confirmed in countless experiments, from the double-slit interference of photons to the entanglement tests that prove non-local correlations. The cat may be metaphor, but the principle is real. Reality at its smallest scales does not unfold deterministically, but stochastically. Now here lies the oddity. If reality can exist as superpositions, then time itself might be subject to superposition. A particle traveling through a closed loop might return to its own past in multiple states at once, one where it interferes with its younger self, another where it avoids it. The universe, rather than collapsing in paradox, could sustain both, like the cat suspended between fates. Some physicists have modeled such scenarios, showing that quantum superposition can, in principle, resolve contradictions that would destroy classical time travel. And here lies the debate. Does quantum theory imply branching universes, as in the many worlds interpretation, or self-consistency within one universe, as in the Novikov principle? Many worlds suggests each outcome of a quantum event splits reality into new branches. A time traveler who attempts to kill her grandfather would not erase herself, but would simply find herself in a branch where she never existed. The Novikov principle insists otherwise. Any action taken in the past was always part of history. You might attempt to change events, but your attempts are woven into the tapestry, ensuring consistency. To imagine this, picture a river that forks. You travel downstream and see two channels diverge. One leads left, the other right. Both exist. Both are real. The many worlds view says you flow into both simultaneously, two versions of you experiencing two outcomes. The Novikov view says there is only one channel, and though you may thrash or paddle, you cannot choose another course. The current carries you inevitably to where you must go. Which of these visions is true remains unknown. Speculation blooms here. Suppose the universe does branch. Every decision, every quantum event, every flicker of uncertainty births new worlds. In such a cosmos, paradoxes vanish, not because they are impossible, but because they are absorbed. Kill your grandfather, and the branch where you exist continues untouched. You have only crossed into another where you do not. Time travel becomes not rewriting, but rewroting. Yet if Novikov is right, then paradoxes dissolve differently. You cannot kill your grandfather, because you never did. The loop is already consistent. Your journey into the past was part of the story all along. Even your attempt at murder is woven into history's fabric, ensuring no contradiction arises. This vision is strangely comforting. Fate as geometry, inevitability as protection. Think of Schrödinger's cat again. In many worlds, both outcomes unfold, each birthing a new timeline. In Novikov's consistency, Only one outcome was ever real, even if uncertainty concealed it. The box is opened, but whichever fate emerges was always destined. Both frameworks allow time travel without paradox, yet they paint reality in profoundly different hues. To feel the strangeness, imagine stepping into a time machine. You emerge in your own childhood home. You reach for the bookshelf, intending to move a cherished object. In one vision, you create a new timeline, a branch where the object shifts, while your original remains intact. In another, you find yourself unable to alter anything in a way that creates contradiction. You may drop the object, but perhaps your younger self always remembered it falling. Fate bends to absorb your interference. Which vision do you inhabit? The universe has not yet told us. And here lies the speculative oddity. Some theorists suggest that quantum mechanics and time travel are not merely compatible but entwined. Entanglement, that eerie link between particles separated by vast distances, may itself be a kind of communication through time. In certain interpretations, correlations appear not only across space but across temporal separation. If so, the cat in the box may be less about probability than about echoes of future and past entangled in the present. This leads to experiments already underway. In 2022, researchers modeled quantum systems where particles interacted with their own past versions. They found consistency prevailed. Paradoxes dissolved into self-adjusting probabilities. It is as though the cat, alive and dead, ensures that whichever outcome you observe, logic remains whole. The box never permits contradiction, even if it allows mystery. Picture standing before a mirror that reflects not only your face but your past self, and perhaps your future one as well. As you lift your hand, so too do they, but with variations. Some movements align, others diverge. The mirror does not shatter. It contains all versions, harmonized. This is the cat in the loop, a metaphor not just for quantum states but for timelines themselves. Yet the debate is far from settled. Many physicists recoil at the metaphysical implications of many worlds. Others reject Novikov's determinism, unwilling to surrender free will. Still, both offer escapes from the paradoxes that haunt classical time travel. Both suggest the universe is stranger than any single line of history allows. Close your eyes. In the darkness, imagine the box. Inside, the cat waits. Its fate is undecided, suspended. That suspension may be the very essence of reality, the ability of the universe to hold contradictions until they resolve, and in that suspension may lie the secret of time travel, the reason paradoxes do not destroy but transform. For if the cat can be alive and dead, then perhaps time itself can be past and future, looped and linear, consistent and branching, all at once. The loop need not be broken. It may only need to be quantum. From here, the journey deepens into law, not human law, but cosmic. If paradoxes are puzzles, then consistency itself may be the answer. Perhaps time is not free to unravel, but bound by principles that protect it. In the next step, we turn to this vision, to the notion that the universe enforces its own coherence, ensuring that whatever else time may allow, contradiction is never permitted. Close your eyes and imagine the universe as a great library. Every book upon its shelves is a history, a record of events etched into the fabric of space-time. You may walk the aisles, remove a volume, and read its story, but you may not alter its words, for the ink is already dry. This is the spirit of the Novikov self-consistency principle, the proposal that if time travel into the past is possible, then the events it allows are always self-consistent. No paradox, no contradiction. Every action a traveler takes was already written into the story. The principle was first articulated in the 1980s by Russian physicist Igor Dmitrievich Novikov, but its roots stretch back through decades of paradox and speculation. Faced with the troubling possibilities of the grandfather paradox, Novikov suggested a radical simplicity. Perhaps the universe enforces consistency. If you go back to kill your grandfather, something will intervene. The gun will jam, the shot will miss, or your grandfather will survive by chance. Whatever the outcome, it will align with the history that already exists. The loop closes neatly, with no threads unraveling. Here lies the fact: in relativity, closed time-like curves, loops in space-time that return to their own past are mathematically possible. If such loops exist, consistency becomes a vital question. Novikov's principle provides a logical shield. Even in loops, events unfold without contradiction. Your presence in the past is not a violation, but part of history's fabric. Now here lies the oddity. Consistency can mean that free will is an illusion. Imagine trying with all your strength to change the past. No matter what you attempt, you succeed only in fulfilling the story that already was. The attempt to alter becomes the reason for the outcome. This feels unsettling, even claustrophobic, as though time itself conspires against you. Yet it may also be liberating. Your journey cannot destroy the present. It only reveals the hidden pathways by which it came to be. And here lies the debate. Do we live in a consistent universe or a branching one? If Novikov is correct, then paradoxes are impossible. But if many worlds is true, then paradoxes dissolve not through prevention, but through proliferation, each attempt creating new branches. In one branch, your grandfather lives. In another, he dies, and you were never born. Both visions preserve logic. Both remain unproven. To picture consistency, imagine a billiard ball rolling toward a time machine. It vanishes into the machine, emerges in the past, and strikes its earlier self, deflecting it away from the machine's entrance. At first glance, paradox: if the ball is deflected, it never enters the machine. Yet simulations have shown that consistent solutions exist. The ball emerges at just the right angle to deflect its younger self into the entrance. The loop closes smoothly. Cause and effect intertwine, but never contradict. Speculation extends to human stories. Suppose you travel back and meet your younger self. You share advice, warn of mistakes, shape a path. Yet when you return to your own time, you find your life exactly as you remembered. Your words were not new, but echoes of advice you already received. You were always the giver as well as the receiver. The loop folds seamlessly, and no contradiction occurs. This vision resonates with myths and legends. In Greek tragedy, prophecies often come true precisely because of the attempts to avoid them. Oedipus, warned he will kill his father, flees home to prevent it, and in doing so fulfills it. In Norse sagas, Ragnarok comes despite every effort to forestall it. The Novikov principle is physics' version of fate, inevitability built not by gods but by geometry. Yet many recoil from its implications. If the past cannot be changed, then what of choice? What of freedom? Are we characters bound to scripts, no matter how passionately we act? Some philosophers argue that consistency does not erase agency. Your choices still matter. They are simply the ones that always were. Just as you cannot choose to be taller or shorter than you are, you cannot choose to alter history beyond what history contains. Consider the imagery of weaving. A tapestry stretches before you, threads crossing in intricate patterns. You may move along the threads, trace them with your fingers, even step into them, but you cannot unweave the cloth. The design already exists. You are both participant and pattern, moving within a structure larger than yourself. Here lies the speculative oddity. Perhaps consistency is enforced not by fate but by probability. Quantum uncertainty might allow countless possible outcomes, but only those that preserve logic are realized. This would mean the universe itself selects self-consistent paths, pruning paradoxes before they bloom. In such a cosmos, the improbable becomes inevitable if it ensures consistency. Experiments have begun to probe these ideas. In 2014, physicists modeled quantum particles interacting with their past selves through closed time-like curves. They found the systems settled into consistent outcomes, even when paradoxical setups were proposed. Later, in 2020 and 2021, researchers extended these models, showing that quantum mechanics naturally favors self-consistency. It is as though the dice rolls of probability conspire to prevent contradiction. Imagine standing at a crossroads in time. One path leads to contradiction, another to coherence. As you take a step, the contradictory road vanishes, leaving only the consistent one. The choice feels free, but the outcome is constrained. The path you walk was always the one you would walk. And here lies the deeper debate. Is this protective principle a law of nature, or merely an artifact of our mathematics? Hawking's chronology protection conjecture suggests quantum effects prevent paradoxical loops from forming at all. Novikov insists they can form, but always resolve consistently. Between these poles lies uncertainty, a question yet unanswered. Close your eyes and sense the weight of inevitability. Every breath you take, every thought you think, was preceded by causes stretching backward into eternity. In the Novikov universe, even your attempts to defy fate are part of fate. The law of consistency is not punishment but protection, ensuring that time does not fracture under its own contradictions. As unsettling as this vision may be, it offers a certain peace. The past cannot be destroyed, the present cannot unravel. Whatever loops exist, they are harmonious. Paradox is an illusion, dissolved by the geometry of reality itself. From here, our journey moves to the guardians who may enforce this protection even more strongly, not by weaving consistency into loops, but by preventing loops altogether. The universe itself may guard its chronology, ensuring time flows forward without rupture. To explore that possibility is to confront the vision of Stephen Hawking, who believed the cosmos has laws hidden deep within it to protect the sanctity of cause and effect. Imagine for a moment that the universe is a fortress. Its walls are invisible, yet unbreakable. Inside, time flows forward, steady and ordered. Outside, if there is an outside, lies chaos, paradox, the collapse of cause into contradiction. The fortress does not invite intruders, it defends itself. This was the vision of Stephen Hawking, who in 1991 proposed the chronology protection conjecture, the idea that the laws of physics prevent time travel on macroscopic scales. In Hawking's words, the laws of physics conspire to prevent time travel. Why did he believe this? Because the alternative seemed unbearable. Without protection, the universe might permit closed time-like curves, allowing travelers to loop endlessly into their own pasts. Paradoxes would fester. Meetings with oneself, attempts to prevent one's own birth, histories unraveling. Hawking believed the cosmos would not permit such instability. The guardian of chronology, though invisible, would stand eternal. Here lies the fact: relativity permits closed time-like curves in theory. Spinning universes, wormholes, cosmic strings, each offers a doorway. But when quantum mechanics is added, strange effects emerge. Energy densities can grow infinite near the would-be time machine, destabilizing space-time itself. Quantum fluctuations, harmless elsewhere, may surge uncontrollably, like storms battering the walls of a fragile tunnel. Hawking argued this runaway effect would destroy the time machine before it could function, preserving chronology. Now here lies the oddity. Time travel seems possible in the mathematics of relativity, but collapses under the mathematics of quantum fields. The very marriage of physics' two great pillars, relativity and quantum theory, may itself guard history. The universe protects its fortress not through a single law, but through the clash of its deepest frameworks. And here lies the debate: is chronology protection a true law, or only a conjecture? Hawking offered no final proof, only reasoning. His calculations suggested that vacuum fluctuations, those restless creations of particle pairs in empty space, would surge uncontrollably near any attempt at forming a time machine. Yet not all physicists agree. Some argue that under exotic conditions, quantum effects might stabilize instead of destabilize. Others note that without a full theory of quantum gravity, the final word cannot yet be spoken. To picture chronology protection, imagine a candle burning inside a glass dome. The flame is fragile but steady, yet whenever you try to open a hole in the glass, wind rushes in, snuffing the flame before it escapes. So too might the universe snuff every attempt to pierce the flow of time. The loophole exists in geometry, but the vacuum rushes in, preventing it from becoming real. Speculation deepens. Perhaps black holes, which seem to flirt with time in their intense curvatures, are themselves guardians. Hawking's own work on black hole evaporation revealed that quantum effects near horizons radiate particles. This Hawking radiation ensures black holes eventually die, preventing eternal paradoxes of information. Some physicists suggest the same principle applies to time machines. Quantum radiation defends the timeline. But others push back.
Could it be that the guardian does not exist universally, but selectively? Maybe large-scale human-accessible time travel is forbidden, but microscopic loops, particles briefly interacting with their own pasts, are allowed. Indeed, quantum experiments suggest such microloops might be consistent. If so, the guardian is not an absolute wall, but a filter, allowing echoes while forbidding cataclysms. To feel this tension, imagine a vast city surrounded by walls. Small birds can dart over, through, or under, slipping unnoticed, but armies cannot breach the barrier. So too might time permit whispers of paradox, quantum echoes, microscopic loops, but prevent the marching armies of macroscopic contradiction. Here lies the speculative oddity. If chronology protection exists, then it may reveal something profound about the unfinished union of relativity and quantum mechanics. The instability of time machines may be a clue pointing toward a deeper theory, the long-sought quantum gravity. Some suggest that any successful theory of everything must explain why time is safe. Others counter that the real revelation will be the opposite, that time is not safe at all, and loops lurk beneath our orderly perception. The imagery is haunting. Picture yourself standing on the edge of a wormhole, ready to step through. As you move closer, the air vibrates, the light distorts, and suddenly radiation floods the passage. The walls of space-time tremble, shake, and collapse. The gateway implodes. You are left alone, with time intact. The fortress holds, and yet doubt remains. In 2005, researchers showed that under certain exotic conditions, wormholes might withstand quantum fluctuations. Negative energy, though fleeting and fragile, could counterbalance the storm. Others explore the role of quantum entanglement, suggesting that space-time itself may be woven from connections that could stabilize loops rather than destroy them. If so, the guardian may not be invincible. The paradox is poetic. If Hawking is right, then time travel is impossible, and our fantasies must remain dreams. But if he is wrong, then the universe may be far stranger, and perhaps more dangerous than we dare imagine. Close your eyes and imagine the fortress again. Its walls are invisible, its gate unmarked, yet every attempt to storm it fails. The defenders are unseen. Quantum storms, vacuum surges, the trembling geometry of space-time itself. They do not reason or argue, they only act, preserving order. But what if the fortress is not absolute? What if the guardian is flawed? Then time may not be a fortress at all, but a labyrinth, one with doors hidden deep within black holes, within strings, within the very foam of reality. The guardian may not prevent time travel, but only make it rare, fragile, fleeting. From here, the journey must venture into stranger terrain. If the laws of physics guard time, do they do so gently or fiercely? Are there cracks in the fortress walls? To search for answers, we must turn to the very fabric of space-time itself, to the foam at the Planck scale, where distance, energy, and time blur into uncertainty. It is there, at the smallest scales of reality, that the fortress may falter, and the possibility of loops may be reborn. At the edge of comprehension lies a landscape we can barely imagine, a frothing, restless sea of geometry itself. This is the realm of the Planck scale, where distance shrinks to hentowana meters, time ticks at hentowana meters,
Time ticks at hemtowanometers, seconds, and energy bends into shapes so fierce that space-time ceases to resemble the smooth continuum Einstein described. Here, beneath the floorboards of reality, lives the idea of quantum foam, tiny bubbling distortions of space and time, fleeting yet ceaseless, as though the universe itself trembles in microscopic turbulence. John Wheeler first imagined this foam in the 1950s. In his vision, space-time at the smallest scales was no placid fabric but a storm constantly reshaping. Wormholes, tiny and transient, might appear and vanish in flashes. Loops of time smaller than atoms might shimmer into existence and collapse before anything could pass through. Though unseeable with present technology, quantum foam offers a picture that the fortress of chronology, so steadfast on human scales, might be porous at its foundations. Here lies the fact. According to quantum mechanics, energy cannot ever be perfectly still. Even in a vacuum, fluctuations erupt, particle-antiparticle pairs forming and vanishing. At the Planck scale, gravity joins this dance, twisting space-time itself into froth. This is no speculation. Vacuum fluctuations have been measured in experiments such as the Casimir effect, where plates in a vacuum experience measurable force from the restless emptiness. The foam itself is beyond direct sight, but its whispers shape physics. Now here lies the oddity. In such a storm, causality itself might blur. If tiny wormholes flicker in and out of being, then microscopic time loops could exist. Particles might borrow time from themselves, weaving through miniature cycles before rejoining the present. These loops would be too fleeting, too delicate to carry a person, but they would hint that chronology protection is not absolute. The fortress may stand tall, yet its foundations shimmer with cracks at scales too small to touch. And here lies the debate: is quantum foam truly real, or only a metaphor born of incomplete theories? Without a complete framework of quantum gravity, we cannot know. String theory paints one picture, where space-time emerges from vibrating loops, smoothing the foam into harmony. Loop quantum gravity paints another, where space-time itself is quantized, made of discrete building blocks that prevent infinite bubbling. The foam remains a frontier, not a certainty. To feel its scale, imagine zooming into a sheet of paper. First you see its fibers, zoom further, and atoms appear, clouds of electrons swirling around nuclei. Deeper still, the quarks inside protons and neutrons. Yet, if you keep zooming, past every known particle, the very coordinates of space begin to flicker. There is no point left to reach. Instead, geometry itself dances like water at a boil. That is the foam Wheeler saw in his mind's eye. Speculation abounds. Could this foam permit shortcuts through time? Perhaps microscopic wormholes, though fleeting, could be stabilized with exotic matter, coaxed into macroscopic passageways. If so, the seeds of time travel would already exist, scattered like sparks across the void, but stabilizing them would require energy beyond our grasp, negative energy densities that exist only fleetingly, as in the Casimir effect, and never yet in abundance. Still, the possibility lingers like a half-remembered dream that time travel's architecture is already written into the smallest corners of reality. Here lies the speculative oddity. If time loops exist in the foam, they might already influence us subtly. Some theorists suggest quantum interference experiments could reveal hints of particles interacting with their own pasts. Imagine an electron passing through a slit experiment, not only interfering with its future and present selves, but also with echoes bent through tiny temporal loops. Could this explain the peculiar persistence of quantum probabilities, the way reality refuses to collapse until observed? Such ideas remain fringe, but they illuminate the strangeness waiting at the Planck horizon. Consider how paradox dissolves here. If loops at the foam scale exist, they may be so short-lived that no contradiction can form. A particle traveling through such a loop emerges nearly instantly, its history intact. The loop is too small to alter large events, too brief to create branching futures. The The fortress remains safe because the cracks are only hairline fractures, never great fissures. In this way, quantum foam could reconcile both visions, allowing loops without destabilizing history. And yet, others warn against over-romance. Foam may be only a placeholder, a way to imagine where our equations falter. Just as ancient sailors pictured sea monsters where their maps ended, we picture foam where our mathematics breaks. The truth may be stranger still, beyond analogy, to ground ourselves. Return to the image of the ocean. From afar, the surface looks smooth. Closer, waves and ripples emerge. Closer still, spray and droplets. Finally, in the mist, particles of vapor. The deeper you go, the wilder the motion. So too with space-time, from afar smooth and continuous, closer distorted by stars and planets, deeper vibrating with fields and particles, deepest, a storm with no stillness. This is the landscape where time's fortress trembles. Close your eyes. Picture the foam not as chaos, but as possibility, a froth of gateways flickering too fast for us to enter. Each bubble might be a whisper of another timeline, each collapse a reminder that even in turbulence, order prevails. The foam is not a promise, but a suggestion. It hints that time is not singular, not absolute, but textured, layered, alive. From here, our journey moves beyond even the foam. If the foundations of space-time ripple with loops, what might happen if we could magnify them, stabilize them, ride them? Could the secrets of travel lie hidden not in vast machines, but in the smallest architecture of the cosmos? To answer, we must step into theories even more daring, to the strings and brains that propose space-time itself is woven from music. There, the possibility of time travel becomes not a violation but a note in a larger symphony. Stand still for a moment and realize this: you are already a traveler in time. Each second that passes carries you relentlessly forward, a passenger on the arrow of time. Yet what is more astonishing is that humanity has already touched the future, not metaphorically but literally, through the fabric of relativity itself. The truth is both humbling and wondrous. Time travel is not merely a dream of fiction. It has already happened, proven not in speculation but in experiments, satellites, and astronauts' journeys across the void. Here lies the fact: time runs differently, depending on motion and gravity. Einstein's relativity tells us that the faster you move, the slower your clock ticks compared to those left behind. Similarly, the closer you are to massive bodies, the more slowly time flows. These are not theories left in chalk on blackboards. They have been measured. Astronauts orbiting Earth age ever so slightly less than those on the ground. GPS satellites, high above the planet where gravity weakens, tick slightly faster, and without correction, your phone's navigation would drift kilometers off course in minutes. The adjustment of clocks for relativistic effects is a quiet but constant reminder that time is not universal but elastic. Now here lies the oddity. Astronauts who return from orbit have truly traveled into the future, not centuries, not decades, but microseconds, milliseconds. Russian cosmonaut Sergei Krikalev, after 803 days in space, had aged about a fraction of a second less than his peers on Earth. It sounds trivial, yet it is profound. By flying through the heavens, he lived in a slightly different slice of time. The future touched him before it touched the rest of us. And here lies the debate. Is this forward time travel all that is possible, or merely the beginning? Relativity allows, in principle, extreme journeys. Imagine a spaceship capable of approaching light speed. A crew on board might travel for a single year, only to return and find that decades, centuries, or millennia have passed on Earth. This is not paradox, but simple consequence. The twin paradox realized on cosmic scales. If such voyages are ever built, then the future is ours to enter, not in fantasy but in engineering. To picture this, imagine a family watching a young astronaut depart. For her, 2 years of flight may pass, For her children on Earth, 50 years unfold. When she returns, she is younger than her children, younger than her grandchildren. She has skipped into their future. The tragedy and wonder intertwine. Her life is stretched across different rivers of time. Speculation deepens. What if civilizations elsewhere in the cosmos have already mastered near-light travel? They might move through epochs as easily as we move through towns. From their perspective, stars evolve in fast forward, galaxies whirl through ages. The universe blossoms and fades in spans that feel like decades. Such travelers would not merely visit worlds, they would visit eras. They could leave at the dawn of a species and return at its dusk, never knowing the centuries in between. Here lies the speculative oddity. In principle, black holes may serve as time machines to the future. Near their horizons, where gravity's pull slows time to a crawl, a traveller could orbit for hours and emerge to find centuries have passed outside. The event horizon is a paradox in itself, a place where time nearly stops relative to the rest of the universe. To hover there is to live in a different clock, to leap into the future simply by waiting. And yet, forward time travel, though allowed and demonstrated, brings with it haunting questions. If the future is already written, waiting to be visited, does this mean it exists now alongside the present and past? This is the block universe model of relativity. All times coexist, stretched across space-time like pages already bound. You do not move through time, you are a thread within it. Your future self already exists, just as your childhood self still exists in another slice. Forward travel reveals not a changing future, but one already etched, waiting for you to arrive. But what of choice? If the future exists, are we prisoners of inevitability, or does our perception, our consciousness, carve time anew with each passing moment? Physicists disagree. Some embrace determinism. Every breath, every decision is already part of the cosmic ledger. Others allow for openness. The future may exist as a cloud of probabilities, not as ink on a page. In this vision, time travel into the future is not arrival at a fixed destination, but the act of collapsing possibility into actuality. Close your eyes. Imagine Earth centuries hence. Cities rise, oceans shift, stars wheel across the sky. You have not lived it, but the equations suggest it already exists, woven into space-time's geometry. Forward time travel is simply stepping into that room, ahead of schedule. To some, this is exhilarating, proof that eternity is real. To others, it is suffocating, proof that freedom is illusion. Yet forward travel has been our companion all along, each satellite orbiting Earth, each atomic clock elevated by a mountain, whispers the same truth. Time is not singular, it flows differently, stretched and squeezed by motion and mass. We are not bound to one rhythm, but to countless overlapping ones. Already, we live in a world where tiny fragments of future travel are essential to technology. Without relativistic adjustments, planes would land miles off course, stock markets would falter, and global communication would collapse. Time's elasticity is not fantasy, it is foundation. Speculation stretches further. Could humanity one day use forward time travel, not just as byproduct, but as tool? Suppose deep space explorers spend a year near a black hole, then return to Earth. To them, a year passes. To Earth, perhaps centuries. They could become witnesses of humanity's distant descendants, leaping forward across epochs as easily as turning a page. The temptation is strong. Why wait for the slow march of history when the future can be touched directly? But here lies the haunting thought. If the future is reachable, then perhaps others have reached it already. Somewhere in the far reaches of the galaxy, travelers may have skipped across millennia. If they returned, they would be out of step with their own civilizations, strangers in futures they cannot predict. For every joy of the leap, there is loss, the loss of all the moments skipped, all the voices unheard, all the lives unlived. This is the bittersweet truth. Forward time travel is possible, proven, real, but it is a one-way road. You can leap ahead, but never back. The past remains sealed, The present vanishes behind you. Each journey forward is a severing, a surrender of what was. Time grants glimpses of eternity, but at the cost of the immediacy of life. Close your eyes again. Feel your heartbeat. Each beat carries you forward, a small but certain leap into tomorrow. You are already a traveler, 1 second at a time. Relativity only reminds us that the speed of our journey can vary, that the arrow is elastic. The future is already touched, every moment, with every breath, and perhaps in ways still beyond our grasp. The touch will one day become a leap, carrying us across centuries as easily as across minutes. From here, our story begins to slow. Having seen the paradoxes, the guardians, the foam, and the touch of the future, we must return. For all its vastness, time is also intimate. It is not only galaxies and equations, but the quiet rhythm of life, the present moment in which we breathe. The final step of our journey will bring us back to that stillness, a soft descent from cosmic speculation into human calm. After so long among the stars, among paradoxes and wormholes and quantum whispers, we return now, not abruptly, not with a jolt, but slowly, carefully, as though descending from a great height. The mind has been stretched across centuries and universes, and it must be guided gently home. Time travel, a dream, a theory, a proof in fragments, has taken us into realms both wondrous and impossible. But all journeys must resolve, and ours resolves here, in the quiet rhythm of the present. Close your eyes and breathe. Feel the simple, undeniable beat of your heart. That pulse is time, not time as Einstein described, not time as Wheeler foamed, not time as Hawking defended, but time as lived, time as felt. For in the end, all speculation about pasts and futures dissolves into this, the experience of now. Here lies the fact. Despite decades of research, no experiment has carried us into the past. Relativity, quantum mechanics, wormholes, cosmic strings, all hint, but none deliver. Forward travel we know, backward travel we suspect. The dream remains unfinished, and yet forward travel itself already reshapes our reality. Astronauts return fractionally younger, satellites tick differently, GPS bends under relativity's hand. Time is elastic, provably so, and that alone is miracle enough. Now here lies the oddity. Though we cannot yet travel back, memory allows us a semblance of it. The human brain is a time machine of its own kind, carrying us to childhood, to moments lost, to scenes replayed endlessly. No paradox arises when you recall your first day of school, or the touch of a parent's hand, or the taste of a meal long past. In these inner journeys, past and present coexist, not in physics, but in consciousness. Perhaps time travel has always been with us, not in machines of steel and light, but in the fragile loops of mind and memory. And here lies the debate. Is time a physical dimension, as real as space, existing in totality all at once? Or is it emergent, born from entropy, from the direction heat flows and order crumbles? Some physicists argue that time may not even be fundamental, but a byproduct of deeper laws, illusions stitched by change. If so, then all our talk of loops and travel may be misguided, chasing shadows of a construct rather than substance. Others insist time is as real as matter, written into the very coordinates of existence. Between these visions, our understanding remains incomplete. To feel this, imagine sitting by a river. You watch the water flow. Each drop passes once, gone forever, replaced by another. This is the time of experience, one-directional, unyielding. But imagine instead a mountain lake, still and wide, where every drop rests together. This is the time of relativity, all moments existing at once, a block where past, present, and future are equally real. Which image is truer? The answer may be both. We experience the river, but the universe may be the lake. Speculation softens here, becoming more intimate. Suppose time travel never proves possible, not backward, not in grand loops or branching worlds. Then what remains? We still hold the power to move forward, not only biologically but creatively. Stories are our time machines, allowing us to relive histories, imagine futures, inhabit possibilities. Science is another. Equations carry us billions of years back to the Big Bang, or trillions of years ahead to the heat death of the cosmos. Through thought, we already traverse spans no machine could carry us. Perhaps the greatest time machine is the human imagination. Here lies a speculative oddity of the gentlest kind. Sleep itself is a form of time travel. You close your eyes, drift, and suddenly hours vanish. You leap into the future without effort, without paradox, carried by the brain's surrender. Dreams themselves are loops, fragments of past stitched into present, glimpses of futures that never arrive. Each night you practice the very thing humanity has long yearned to master. And so we return again to breath. The grand paradoxes, the cylinders, the wormholes, the foam, they inspire awe, but they remain distant. What is close, immediate is this: the sound of your inhale, the weight of your body, the pulse of life within you. Time is not only cosmic, it is personal. It is the span of a life, the arc of a story, the rise and fall of a chest in the dark. Close your eyes once more. Feel how vast the universe is. Galaxies wheeling, black holes spinning, strings and quanta vibrating at scales you cannot see. And yet, within all of that immensity, here you are, not in yesterday, not in tomorrow, but here. This moment, too, is eternity. And here lies the final debate. Should we continue to chase time travel, to pour thought and energy into paradoxes, or should we accept the gift of now? Some argue that the pursuit itself elevates us, that the quest for impossible knowledge defines what it means to be human. Others whisper that the truest wisdom is not in conquest of time, but in surrender to it, to live fully in the present without regret for the past or hunger for the future. Imagine a gentle return from orbit. The stars fade, the blue curve of Earth swells below, clouds drift across oceans, the spacecraft hums as it re-enters atmosphere, slowing, softening, returning to ground. This is how our journey ends, not with a leap, but with a landing. The cosmos remains vast, full of riddles, but your place within it is here, now alive. So let us end with stillness. You have walked the paradoxes, touched the future, glimpsed the foam of creation. You have seen time as river, as lake, as storm, and now you return to the simplest truth. Time is also a breath, a heartbeat, a moment unfolding in silence. Rest here. Rest in the knowledge that time, however strange, carries you forward always. Rest in the comfort that you are part of its flow, inseparable from the great fabric. Rest in the wonder that every moment is both fleeting and eternal. Sleep now, traveler. The past is safe, the future awaits, and the present holds you gently. Whatever else time may be, it is also this, a cradle rocking you into rest.